Hello everyone, this is Tom Whitaker. I'm here with Andrew Slate. We're located in the Biological and Agricultural Engineering Department on the campus of North Carolina State University. We want to thank Dave Hoisington and Jamie Rhodes for putting this session together and inviting us to speak about detecting mycotoxins in bulk commodities using sampling techniques. Dave and Jamie are with the Peanut and Mycotoxin Innovation Lab located in Athens, Georgia. Andy and I used to be employed by the Agricultural Research Service of the U.S. Department of Agriculture. After 42 years, I have retired from ARS. Our unit was physically located on the campus of North Carolina State University. So when we retired, we continued our research here in the Ag Engineering Department. What I hope to do this morning is to share with you some of the important findings of our research, and hopefully you'll be better informed on the topic. We're going to present the information in three segments. I'll present the first segment, and then Andrew will present the second and the third section. When regulatory agencies such as our Food and Drug Administration establish maximum limits for mycotoxins in foods and feeds, there's a ripple effect back through a commodity supply chain. Various members of the supply chain will test their product for the mycotoxins and try to determine if they test below the regulatory limit or not. What happens often is the buyer will tell the seller, don't ship me a product unless it tests below a certain maximum level, which may be a regulatory limit, or it may be an industry standard, for example. So the seller will go out and he will test his product before he ships it. If it fails, he'll pull it from the supply chain. If it is acceptable, he'll send it on to the buyer. What the buyer and the seller will do is they take a small portion called a sample from the lot, and they will test the mycotoxin level in that sample, and they'll make an assumption that the lot is equal to whatever they measure in the sample. Then, if they're in a regulatory environment, they'll compare the sample concentration to some maximum level, such as a regulatory limit, and they'll accept the lot if it tests below the maximum level, and they'll reject it if it tests above the maximum level. One of the missions of our research unit here was to help our sister agency, the Agricultural Marketing Service, and commodity industries to do a better job of measuring grade and quality factors, and measuring mycotoxins fell under this mission. And so we would often get calls from laboratories or inspectors in the field telling us that they were concerned about the results of testing, in this particular case, peanuts for aflatoxin. And I can remember getting calls from the field, and they would say, we took 3 5-kilogram samples from the same lot and we got 2 zeros and 100 parts per billion. What are we doing wrong? There was so much variability in the results that they assumed right from the very beginning that they were doing something wrong. And we really didn't know what the problem was. We tended to focus on the analytical method, but we realized that we knew very little about the system of testing bulk lots for mycotoxins. In this particular, it was testing peanuts for aflatoxin. So I was asked to begin a research program to try and figure out why it was so difficult to get an accurate estimate of the true concentration in a bulk lot. And what we did was we went out and found commercial lots that were contaminated with aflatoxin, and we started out in shelled peanuts and went on to shelled corn or shelled maize, and then on to cottonseed. And what we did was we took replicated samples from the same lot, and this is an example of where we took 16 1.1 kilogram samples, that's about 2.5 pounds, from the same lot. And I've ordered these 16 sample test results from low to high just for ease of viewing. And you'll see that for this particular lot, that the 16 samples varied from 0 to 90 parts per billion. And our best estimate of what was in the lot is the average of these 16, or the 25 parts per billion. So we learned immediately two important things from this data. First of all, we learned that there was inherently just a great deal of variability among sample test results taken from the same lot. In this case, you see the sample values varied from 0 to 90 parts per billion. So we knew then that these inspectors and these laboratories in the field were probably not doing anything wrong. They were just dealing with the inherent nature of the testing lots for mycotoxins, and that there was just inherently a lot of variability in the system. The next thing we learned was that the distribution of these sample test results is not symmetrical about the lot concentration of 25 parts per billion. You'll notice that that 8 plus 2 here, that 10 of the sample test results are below the lot concentration of 25 parts per billion, and only 6 of the 16 sample test results are above the lot concentration of 25 parts per billion. So we learned, secondly, that the distribution among these sample test results coming from a lot is skewed, and in statistical terms it's positively skewed, because there's a greater number of sample test results below the true lot concentration than above. Now, the implications of this is that if you were to take a single sample from a lot, you're more likely to get a sample value below the true lot concentration than above the lot concentration, which will tend to give you a sort of a false sense of security as to what's truly in that lot. The next question we had was, what is the source of this variability? Why do these samples vary from 0 to 90 parts per billion? And to determine that, we turn to the mycotoxin test procedure, the method used to get a sample test result. And the test procedure here in the red box is made up of 3 steps. There's a sampling step where you take the sample from the lot. Then there is a sample preparation step, which is a 2-stage process where you grind the sample in a mill, and then you take a small comminuted test portion from the mill. So you have another sampling step, and then there's an analytical step where you extract the aflatoxin or the mycotoxin from the test portion, and you quantify the mycotoxin in that test portion, and you finally get a sample test result. So we felt that this variability that we saw in the previous slide, where the samples vary from 0 to 90, that the sources of error had to come from one or more of these 3 steps in the mycotoxin test procedure. So our error model that we put together was that the total variability that's associated with the mycotoxin test procedure had to be the sum of the errors associated with sampling, sample preparation, and analysis. Now, it's important to know how much each of these steps contribute to the total variability, because each step there's a different cost associated with reducing the variability of each of these steps. And so we next designed our experiments to try to partition this total error into the sampling, sample preparation, and analytical errors. And this next slide gives you an example of the variability associated with each step of the test procedure. We took a lot of shelled maize at 20 parts per billion, and our mycotoxin test procedure consisted of a sampling step, which was 1 kilogram. Our sample preparation step consisted of grinding that 1 kilogram sample in a roamer mill, and then removing a 50-gram test portion from that comminuted sample. And then finally, our analytical step was to extract and quantify the aflatoxin in that 50-gram test portion using high-performance liquid chromatography, or HPLC. Now, our measure of variability, we use variance. Variance is just one of several statistical measures of variability. We could have used standard deviation or relative standard deviation, but we decided to use variance because variances are additive, and for example, and standard deviation is not. So you'll see here that we did get a variance for each step of this test procedure. The sampling step, we had a variance of 241. Sample prep, we had 56, and for HPLC, a little over 4. Now, the bigger the number, the more variability that you have in the system. And so you could add these three variances up, and our total error was 302.7. So the next thing we learned was that all three steps contributed to the total variability associated with the mycotoxin test procedure. The next thing we learned that for small sample sizes, the sampling variance tended to be the greatest source of error. And in fact, in this case, we found that using a 1 kilogram sample, that the sampling step contributed about 80% of the total variability. The sample prep step contributed almost 19, and the analytical step just a little over 1% of the total variability. So it's interesting here that back when we were asked what was going on, we tended to focus on the HPLC, or the analytical method, which was probably the incorrect way to look at this, because most of our error tends to be in the sampling step. So the next question was, why is there so much error associated with the sampling step? And the picture that we were able to paint was that the sampling step has so much error because of the mycotoxin distribution among kernels in the lot. We were able to paint a picture that said that a very small percentage of the kernels are contaminated, and those kernels that are contaminated can vary in the amount of contamination from very little to extremely high levels. It's been reported in the literature, for example, as much as 1 million parts per billion on a single peanut kernel. So you can see intuitively that if you've got sort of a needle in the haystack problem, you've got very few kernels contaminated, so when you take a sample, there's a chance that that you'll miss the contaminated kernel and your sample will show 0 parts per billion. But there is also that chance that you might hit that hot kernel, that kernel with a lot of mycotoxin on it, and then you'll have a sample with a very high level or high concentration of mycotoxin. So this is why we think there's so much variability associated with the sampling step. It has to do with this extreme distribution of contamination from kernel to kernel. The next thing we learned was that these variances that we show for this specific test procedure of 1 kilogram sample and roamer mill, 50-gram test portion, and using HPLC, was that these variances are unique to the lot concentration of 20 parts per billion. We went out and got lots at various aflatoxin concentrations, and we then measured the variance for each of these lots, and we found that indeed the variance for each of those steps increases with lot concentration. Now this slide is just for sampling variance, but we got the same response with sample prep and analytical variance, and that the variance or the amount of error or the amount of variability increases with lot concentration. So that means that if you take a lot at a much higher concentration, you'll have more variability than a lot at low concentrations. So the question is, how do you go about reducing this variability for each of these steps? And to show you how to reduce sampling variability, you simply would increase the sample size or the number of samples taken from the lot. To reduce the sample prep variability, there are two ways, because remember it was a two-step process. First of all, you can just grind the sample into a finer particle size. The finer the particle size, the more homogeneous and the more particles that you have per unit mass. The second way to reduce the sample prep variability is to increase the test portion size, because again, remember, it is a sampling step, and if you increase the test portion size, you will also, for a given grinder, you will decrease the sample prep variability. Now you can decrease the analytical variability by increasing the number of measurements that you take on the test portion and averaging the number of measurements. You could also decrease the variability by using analytical methods that have improved technology. For example, we found that high performance liquid chromatography had a lower variance than thin layer chromatography. So to give you an example of how to reduce the variance, I've taken our original estimates of variance for the 1 kilogram sample, the 50 gram test portion, and the making one measurement using HPLC. And we've gone to a test portion now where we increased the sample size from 1 kilogram to 3 kilograms, and we have reduced the sampling variance from 241 to 80. There's a statistical law that says if you double sample size, you'll cut the variance in half, or if you triple sample size, you'll cut the variance by a third, and you'll see that's exactly what's happening here. When we go from 1 kilogram sample to 3, we reduce the variance to 80. And also when we increase the test portion size from 50 to 100, we reduce the variance from 56 to 28. We cut it in half as we double the test portion size. And when we make two measurements on the test portion and average them, we cut the analytical variance in half. So when we sum this up now, we see that our total variability now is 111 as opposed to 302. So there should be a lot less variability with the second test procedure than with the first, because our overall variability or error associated with the second test procedure is 111 compared to 302. Now it's this variability obviously that it causes all of the problems, and when you have the variability in the with the mycotoxin test procedure, what will happen is that you're going to make two mistakes with your sampling plan. This variability leads to the misclassification of lots. There are two types of mistakes that you'll make. First of all, good lots will be rejected by your sampling program. A good lot being one that has truly got a concentration below the maximum level, but when you take a sample from it, the sample value is greater than the maximum level. So the sample says this is a bad lot, and so you reject that lot. I call this the seller's risk because these lots are pulled from the supply chain at an unnecessary expense to the seller. The second type of mistake is a bad lot being accepted by the sampling program. You'll have lots that are truly bad, they truly have concentrations above the maximum level, but when you take a sample from them, the sample value will be below the regulatory limit, and so you'll accept this lot and it will go on down the supply chain. I call this the buyer's risk because this lot now will be accepted by the buyer, and he may add value to the lot before and if the lot is later caught as it goes down the supply chain. To give you an example of these two, of the magnitude of these two types of risks, if we look at the next slide, I took some of our actual data. This is a lot of shell corn where we estimate that the true amount of aflatoxin in the lot is at 11 parts per billion. And these are the 16 sample test results that we took from that lot. And if we were to use a sampling plan where we'd take a 1.1 kilogram sample from the lot, we would prepare it and analyze the aflatoxin in that sample. And if the sample tested less than 20, we would accept the lot. If it was greater than 20, we would reject the lot. Now this is only an example, but if we say now, how many times would we have accepted this lot and how many times would we have rejected this lot with this sampling program? So we simply look at our 16 sample test results, and we look at how many times would we have gotten 20 or less in our sample test results. And you'll see here that we would have gotten 20 or less 8, 9, 10, 11, 12 times out of 16. So in other words, 75% of the time when we use this sampling plan on this lot at 11 parts per billion, we would have accepted this lot as we correctly. But you'll notice that 4 times out of 16 we got sample values greater than 20. So we would estimate that we would have rejected this lot 25% of the time with this sampling program. So an estimate of the seller's risk, or the good lots rejected, is 25% associated with this sampling program when sampling a lot at 11 parts per billion. Likewise, we can now look at a bad lot by using our U.S. Food and Drug Administration maximum level of 20 parts per billion. Using the same sampling program, taking a 1.1 kilogram sample from the lot, and if it tests less than 20, we would accept it. If it tests greater than 20, we would reject it. And if we look at our 16 sample test results, this being a bad lot, we would hope to reject it all of the time, but you'll notice that 8 times out of 16, we actually got a sample test result below 20 parts per billion. So we would have accepted this bad lot 50% of the time, 8 times out of 16 we would estimate. And we would have correctly rejected this lot 8 times out of 16, or 50% of the time with this particular sampling program. So what happens in any market system is lots come down the supply chain. These lots vary from 0 to some high level of concentration, and each lot is tested as it comes past a point in the supply chain with a sampling program. Some of the lots are good, that is, they truly have concentrations below the regulatory limit, and when they are sampled and tested by the sampling program, some of those lots are accepted, which is a correct decision. but some of those lots are rejected, which is the seller's risk. And also some of the lots coming down the supply chain have concentrations greater than the regulatory limit, which we would call them bad. And when sampled, the sampling plan would say they are truly bad and they would be rejected, which is a correct decision. But then sometimes some of those lots would be accepted by the sampling program and they would be accepted, which we call the bad lots accepted or the buyer's risk. So you've got a certain number of these good lots being rejected and a certain number of these bad lots being accepted as they come down the supply chain. And what you would like to do in the design of any sampling program is to minimize the buyer and seller's risk. And in fact, what you would like to do is accept 100% of the good lots, and you would like to reject 100% of the bad lots, or accept none of the bad lots. Accept plus rejects equal 100%. So if I graphically show you what we would have in a perfect sampling program where we would accept 100% of the good lots and reject 100% of the bad lots, graphically it would look like this. This curve shows that we would accept 100% of the good lots. We just added a vertical axis now to the previous slide, which is lots accepted. In a perfect sampling plan, we would accept 100% of the good lots, and then we would accept none or reject 100% of the bad lots. Now this curve is called an operating characteristic curve, or an OC curve for short. And it can be used to evaluate the performance of a mycotoxin sampling plan, and it gives you some idea of the buyer's and the seller's risk. In this case, with a perfect sampling program, the OC curve shows you that you accept 100% of the good lots, which means you have no seller's risk, and you reject 100% of the bad lots, which says you have no buyer's risk. But what happens in reality is, because of the variabilities that I showed you earlier, we get an OC curve that looks like this curve of dots, in which you would accept less than 100% of the good lots, and you would continue to accept some of the bad lots. And this is typically what we see, the type of OC curve we see for mycotoxin sampling plans. And this little area above the OC curve and below the regulatory limit is indicative of the seller's risk. This area up here is related to the good lots rejected, and then this area under the OC curve to the right of the regulatory limit is indicative of the bad lots accepted and is indicative of the magnitude of the buyer's risk. So when we're asked to design the perfect sampling program, there is no such thing as a perfect sampling program. You really are saying how much risk are you willing to accept, and then you try to design your sampling program to minimize the seller's risk and the buyer's risk. So it's very important that we be able to calculate this operating characteristic curve, or OC curve, for any given sampling program. Then we can share with the buyer and the seller the magnitudes of the two risks associated with the sampling program. And we, working with the Department of Statistics here on campus, we developed a method to calculate the OC curve if we could describe this variability among sample test results and the distribution among these sample test results as a function of the mycotoxin test procedure. And what we put together was a model by which the user could input his test procedure, that is the sample size, the sample preparation method, his analytical method, and he could input his accept-reject limit. And then inside the black box you would have this information about the variability and the distribution, which were measured experimentally, but then along with some statistical theory, then we could calculate the operating characteristic curve and give the user an estimate of the Bayer's risk and the Scheller's risk. And if with a little bit more information we could input to the model, which I'm not going to talk about here today, is we could also indicate how much mycotoxin has been removed from the supply chain, and you can get some estimates of the cost associated with your sampling program. Now, to date, we have measured the sampling statistics, which is the variance components, and measured the distribution, and are able to calculate the OC curve for about 20 different mycotoxin commodity combinations, and you'll see the ones that we've studied to date in this table. Now, being scientists, we just don't go out and decide exactly where we're going to measure sampling statistics. Often we are working at the request of government agencies, whether it's U.S. Department of Agriculture or our Food and Drug Administration, and also working with commodity industry requests. We will develop these research studies to get at the sampling statistics for these particular mycotoxins and commodities. And you'll see that we're heavy on aflatoxin because that is considered perhaps the most carcinogenic of the known mycotoxins. And we originally started here with shell peanuts, and but you can see now that we have gone into several grains, several tree nuts, and several others such as cottonseed, herbs, and dried figs. Now, in the last 15 years, the request for this information has come from Codex, and in fact, the Codex has been working on harmonization of aflatoxin maximum limits and sampling plans for about 6 different commodities: shell peanuts, the 4 tree nuts, and the most recent is dried figs. And we worked with the various agencies to develop the sampling statistics, and these statistics have been used by Codex to develop harmonized maximum levels and sampling plans. What I'd like to do next is to show you how the model works and how it generates an operating characteristic curve, and how to go about reducing the accept-reject limit. And I am going to use, just as our example, testing lots of shelled corn for aflatoxin. For the example, we'll use the US FDA regulatory limit of 20 parts per billion. And our sampling plan will be where we'll take one 1 kilogram sample from a lot, we'll grind it in a roamer mill, and we'll remove a 50-gram test portion, and then we will quantify the aflatoxin in the test portion using HPLC, and then we'll compare the accept-reject limit, or the sample test result, to an accept-reject limit of 20 parts per billion. And we'll accept the lot if it's below 20. We'll reject the lot if it's above 20. And with the model, we would calculate an OC curve that looks like this. The vertical axis is the chances of accepting a lot, and the horizontal axis is a lot concentration. So this OC curve that was generated by the model tells you what are the chances of accepting a lot at a given concentration by this sampling plan. For example, if this sampling plan sampled a lot at 10 parts per billion, you would expect it to accept about the chances of accepting that lot to be about 85%. That means the chances of rejecting it are about 15%. And you can look at other lot concentrations when you take this sampling plan and sample a lot at 30 parts per billion, you would expect to accept about 40% of those lots at 30 parts per billion and reject about 60% of the lots at 30 parts per billion. So an indication of the seller's risk is this area above the curve and below the 20 parts per billion, which is the regulatory limit. This area above the curve is indicative of the good lots rejected. And you can look at any lot concentration and look at the chances of rejecting this good lot. Also, the area under the curve and to the right of the regulatory limit is indicative of the buyer's risk. This shows you what are the chances of rejecting, or in this case, accepting a bad lot. Now, if you don't like the magnitudes of these risks, then you can change your sampling program to accept, to see what the OC curve would do to change the buyer's and the seller's risk. And the first way that you can there are three different ways to reduce the buyer and seller's risk. And the first way is just to reduce the variability of the mycotoxin test procedure. Now recall, there are three ways to reduce the variability. You can reduce the sampling variability, sample preparation variability, and the analytical variability. But recall, generally the sampling step is the largest source of variability, and quite often you'll see this is the first place that users will go to reduce the variability of the mycotoxin test procedure. So what we'll look at here is what is the effect of increasing sample size on reducing the buyer and the seller's risk. If we start again with our sampling program where we take a 1 kilogram sample and we will accept the lot if the sample test result is below 20. But if we increase the sample size of that sampling program from 1 kilogram to 5 kilogram, we now calculate what the OC curve will look like, and you'll see that the black line reflects a sampling program that uses a 5 kilogram sample. And you'll notice that now the chances of rejecting a good lot have decreased, and the chances of accepting a bad lot have also decreased. So by reducing variability, or increasing sample size in this case, has reduced both the seller's risk and the buyer's risk. And you'll notice that this curve is getting steeper and steeper. So what would happen if you kept increasing sample size, you would start approaching that perfect sampling program where you have a very small seller's risk and a very small buyer's risk. But remember, you're still carrying along, in this case, the amount of error that's associated with sample preparation and analysis is still there, even with the 5 kilogram sampling program. The next way we can reduce these risks is to use an accept-reject limit below the regulatory limit. Now, it's not uncommon for the buyer to say, well, I'm having to develop product to meet the FDA guideline of 20 parts per billion, so don't ship me any product that tests more than 10 parts per billion. I just use that as an example. And so what they're doing is they're telling the seller, I want to use an accept-reject limit lower than the regulatory limit. And so we go back to our friend here, the same sampling program where we take one kilogram sample. If it tests less than 20, we will accept the lot. Now, if we lower the accept-reject limit to 15, you'll see the OC curve now for a 15 accept-reject limit shifts to the left. And what that does is it reduces the chances of accepting a bad lot, but it increases the chances of rejecting a good lot. So when you use an accept-reject limit below the regulatory limit, in this case a 15 less than a 20, you do reduce the buyer's risk, but the penalty you pay is you increase the seller's risk. And if we continue this and use an accept-reject limit of 10 parts per billion, you'll notice that the OC curve continues to shift to the left and continues even further to reduce the buyer's risk. So the buyer is really putting a lot of the load on the seller. He's saying, I want to reduce my risk, but the penalty you're going to have to pay is you're going to have a higher seller's risk. There are greater chances of rejecting a good lot. The next way, the third and final way to reduce the risks associated with the sampling program is to increase the number of samples that are tested or taken from a lot. Now, this particular plan, you do not average the results, but you say all of the samples have to test less than the accept-reject limit. If you say just average them, it's nothing but increasing sample size, which I showed you in the previous slide. But this particular method says that all three or all samples, excuse me while I go back, that you're saying that all samples have to test less than the accept-reject limit. And if we look at the example, we start again where we use 1 kilogram sample testing less than 20. But if we say let's increase the number of samples that we're going to test to 2, and both of those have to test less than 20, then your OC curve looks like the one here in black. You'll notice the OC curve shifts to the left. And it does a similar effect as the previous slide in that it reduces the buyer's risk, the chances of accepting a bad lot decreases, but the seller's risk increases. And if we go to 3 samples where we say all 3 have to test less than 20 to accept the lot, the OC curve shifts even further to the left, and you continue to reduce the buyer's risk, but at the expense of increasing the seller's risk. Now, this type of testing program is used in the European Union and also now by Codex, and it does give a great deal of protection on reducing the bad lots accepted. This type of testing program is also used in the United States when they export to the European Union, because it's quite expensive to have a lot tested in Europe and it be rejected. So they like to decrease the number of lots rejected when retested in Europe, and so this type of testing program is used on export types of programs. So just to recap, there are 3 ways to reduce the buyer and seller's risk by manipulating the sampling plan parameters. First of all, you can reduce the variability of the mycotoxin test procedure, such as you can increase sample size. The second way is to use an accept-reject limit that is lower than the regulatory limit. And finally, you can increase the number of samples where all samples has to test less than the accept-reject limit. So I want to close out this session and just say again that there is no perfect sampling plan. Sampling plan design is generally a compromise between cost and of the plan and the level of risk. There's only so many resources in the when you're trying to design a sampling program, so it's a matter of how do you minimize the risks as much as possible for the resources that you have on hand. And my last slide is links to two websites. The bottom website is a link to our website that was established while we were with ARS, and it has all our publications on the subject, and they're open domain, so they're there to support the information that I've just given you. And there's also another link here. I mentioned that we had developed a model, and Andy's going to talk about this model. The FAO wanted a mycotoxin sampling tool to calculate OC curves, and we offered the model to them, and they accepted, and they now support the model, and you can get at the model through this web link, fstools.org. Thank you so much, and Andy will be presenting the next two sessions.